Hey, I'm Mike Lipkin from Isothermal Community College. We're here today to talk to you guys about the Galilean ramp that we've built. At any rate, we have a ramp system where we're going to release a ball from a certain height, and we have the conservation of momentum. The initial energy of the ball is going to turn into the final energy of the ball. The initial energy of the ball is all potential energy, mgh. That's going to get turned into kinetic energy, 1/2 mv final squared, and it's going to get turned into rotational motion for the ball rolling, which is 1/2 I omega squared. Now we know that V final is equal to omega final R, and so we can substitute in here for omega final. We can substitute in here for I. We can then solve for V final. When we do this, using the height of 22 centimeters for our ramp, we find that the final velocity of the ball should be 1.75 meters per second. If the final velocity of the ball is 1.75 meters per second and the track is 2.43 meters long, then it should take 2.78 seconds for the ball to track down the entire track. So that's one of the first things we could do, is let's watch and see if it takes 2.78 seconds for the ball 1 to reach the end of the track. Go ahead. So now I'm going to turn it over to a student. This is Joshua Pullman. He's going to show you and demonstrate the Galileos Ramp for you.
So this ramp, we can see, is about 22 centimeters above the ground and about 2.43 meters long. So how it works is one ball is placed here and released, goes and hits this here auto gate, which releases the next ball, which then goes down and hits the next auto gate and releases the last third ball. And if our timings are correct, each ball will be at these 3 points at the same exact time.
Okay, so as you're watching the film, see if the ball impacts the 3 bells at the same time. If we have this right, then the 3 bells should ring at the same time.
Timothy Hutchins, and we're going to show the Galilean ramp work.
Okay, here we go. See if the ball... The question is, did all 3 bells ring at the same time?
So, measuring these positions, we have 28 here, 112, and 215.
Okay. So you'll notice that, of course, these measurements are much more consistent with the second formula, meaning that distance is a function of time squared. Thank you, Galileo. Roll it. It's weird that we'd want it to be slow, but it just helps. Okay, rolling.